asymptotic analysis of algorithms, I guess A. And this involves what is commonly known as big O notation. There's more than big O, there's also theta and omega. So the way to the way to think about this is especially in the context of data structure. So we had this, we had this ADT, this specification. For example, for a list, we wanted something like find, insert, delete, so on and so forth. And we have a data structure which is an implementation. So note that if you, for example, like in the Shakespeare assignment, you had a collection of words and you want to find, insert, and delete, you can use a linked list. You could also use an array. You could use a hash map. You could use a binary search tree. You could use all these different data structures, right? And you could get the same functionality. So although your implementation would be different, you could still solve the assignment using any data structure. So the question that comes up is, what is the best, or really the most efficient data structure? So maybe best is the wrong word here. What I really mean is the most efficient. And so we need a mathematical discussion of what is the most efficient data structure. Alternately, you could consider some computational problem. Suppose you took sorting. Right? So sorting n numbers. So given an array of length n, sort the numbers in, let's say, increasing order. And it's, it's likely that many of you have seen different algorithms. Yeah? So I will define that right now. So I'm going to define exactly. So that's mathematically it's ill-posed because I haven't told you what I really mean by efficient. Although you have some sense of efficiency, right? So the most obvious one is what's called wall clock time. You can profile two different data structures, and you can see which is faster. That's one notion of efficiency. That's what's called an empirical notion, right? It's like you run an experiment and you see which is better. And what we'd like is some kind of mathematical theory behind it. Can we decide what is the most efficient data structure without actually having to run experiments, right? So you have many different algorithms for this problem, and I'll talk about some of these later on. You have selection sort, insertion sort, merge sort, etc. And you could, in quicksort, you could ask which is the best algorithm or the most efficient algorithm. And so what the asymptotic analysis of algorithms does is it gives a mathematical language to talk about this. So interestingly, just like a sort of minor history lesson, what is the oldest algorithm that we know of historically? Does anyone know? Yeah? Carry-on addition. Maybe, okay. Although you know that's interesting. The carry-on addition needs a place value system, right? Like if you represent numbers in Roman numerals, then you can't do carry-on addition. So which means that carry-on addition probably came up when people designed a place value system where they actually wrote numbers in that way. And that was maybe, I don't know, it started in India maybe about 2,000 years ago. Or maybe not even 2,000, maybe like 1,500 years ago. There's something even older, a classic algorithm. Yeah? Sorry? Towers of Hanoi. That's an interesting one. I don't know. I don't know when to date that. That might be there. Have any of you heard of Euclid's algorithm to find the GCD? I mean, Euclid, that's probably about 2,000 years old, right? So what's very interesting is that even though they had no notion of efficiency of algorithms, Euclid's algorithm is the most efficient algorithm to find GCD. Like it actually, so people sort of kind of had this notion of efficiency, but not explicitly, in like how do you add two numbers? How do you multiply two numbers? And coming up with different algorithms. And it was only in the 1950s and 60s that mathematicians, like, okay, the notion of an algorithm itself has been around, well, was codified probably in the 50s and 60s. And I guess there's a sort of well-known mathematician, computer scientist called Knuth, and this was probably 60s, 70s, so Knuth. There's also Blum. And so what they were doing was trying to come up with a mathematical way of describing what it means for an algorithm to be fast. And a lot of this theory emerges from that time. So from a mathematical standpoint, it's not that old. Although you might think 60s and 70s is old, but if you think about calculus, calculus is even much older. Okay, so how do we, I'm going to introduce some notation. Now I'm going to take it slowly here, but I want to make sure that you understand all the notation before we discuss what big O notation is. So somebody asked, what do you mean by efficient? So I'm going to write a definition here. So given an input x of length n. So the way to think about this could either be an array or it could be a linked list. It could be a stack. It could be whatever data structure you want. So think of the input as the object that your algorithm is processing. This is the size of the input. So we can say count the number of elementary operations that algorithm script A performs on X. Okay, so there's a lot of words here. So the way to think of this is, suppose I'm doing find in a linked list. What is the input defined? It's a linked list and a number, right? So the number is really like constant size. So the length of the linked list is the size of the input. Now you can look at your code that goes ahead and finds in a linked list, and you can count how many operations that code performed on this input. So what does your find look like? Your find looks something like this, right? So find on a linked list, it's going to be something like while current not equal to null, if current arrow data is equal to val. In this case, what you would do is you would return current, else current is equal to current arrow next. Something like this, right? There's some initialization and then there's this code. Does that make sense? So each line of code is an elementary operation. Checking these pointers, that's an elementary operation. Then checking these, that's an elementary operation. Return is an elementary operation. So you can think of elementary operation as like lines of code executed, right? So suppose you're running this piece of code to find on a linked list. How many elementary operations will this piece of code perform to find? Yeah? At most n. Maybe, yeah? N times 3 or at most n times 3. It could be faster. If you're lucky, maybe it'll do it in 10 operations if the element you're trying to find is at the beginning of the list, right? So it's a little hard to pin it down exactly. But you can say it's going to be at most, I don't know, n times 3 or n times 4. Because realize that even though it's only 1, 2, 3, 4 lines of code, there's a loop. So the number of times that a line is executed could be a lot. And what you're counting here, number of elementary operations, is kind of like the number of lines of code executed and no function calls. I mean, function calls are going to complicate the picture, because if you have a function call, then you have to go and count how many lines of code in that function are being executed. Yeah? Well, yes. So, but you can think of that as each line. This is like a comparison, which is like a line of code. So each line of code is, for those of, I guess you all know assembly, right? So when this gets when this is converted to assembly, like each instruction in assembly is what it's like add or jump or, or compare or something. So it's almost like counting the number of lines of assembly that would be executed. Does that make sense? So that is what I mean by count the number of elementary operations that the algorithm performs on X. You could have a different algorithm, and it would potentially be different. You could have a different question. Instead of finding in a linked list, maybe you want to insert. Or maybe you want to sort on an array or whatever. Note that if you're inserting in a linked list, it's only 4 lines of code that are going to be run, 4 or 5, right? It doesn't matter how long the list is. Does that make sense? Okay. So I'm going to write some notation here. I'm going to say RT subscript A on X. This is the running time of the algorithm A on input X, where again running time is the number of elementary operations. So this is just some notation. I'm just going to call it, so script A is an algorithm, little x is an input. Okay, now for sort of the main definition, the worst case running time, sometimes this is also called the time complexity of A. The worst case running time of the algorithm is a function that I'll do T subscript A of n. Okay, so technically it's a function T sub A going from natural numbers to natural numbers. If that bothers you, don't worry about it, I can explain it. Is the max, okay, so pay attention, is the max over all x of length or size n. So we just consider the length of RT of A of x. Does this make sense? So let's like parse this, right? So what this is saying is this function is called the worst case running time. So the worst case running time is not a single time, it's a function. It's a function of natural numbers. So it takes a natural number n, and it says you look at all the inputs of length n and look at which was the largest runtime. That is the worst case running time. And you can say technically this is also length at most n, but we'll stick with this. Okay? Does this make sense? Right? Yeah. This is x of length or size n. Right? So the idea is that if you look at this quantity here, RTA of x. This is parametrized, or the argument of this function is an input. In the worst case running time, the argument is an integer. Well, it's a natural number, because you're only looking at the worst case input for each size. So this function, you could imagine plotting this function. Right? So you could plot TAN, and it's going to do something, right? I mean, okay, it's probably monotone, but it might not be a well-behaved function the way you and I know it. What is a well-behaved function? Like a mathematical function that you study in calculus, like a polynomial. So this function may have like some strange behavior. Maybe at even, it's going to do something different than odd, like you have like off by one things, right? So maybe your function looks like this. Could look something like that. Now you could imagine that if you have two different algorithms, yeah? X is not an integer. X is an input to the algorithm. N is the size. Sorry, say that again? Yes. Yes. I'm giving you examples. Meaning that no, it's an input for the algorithm. Now, if you do find on a linked list, the right way to think about it, okay, instead of thinking about it from a C++ standpoint where it's a method inside the class, think of it from a C standpoint. What is the input to that algorithm? That algorithm needs the linked list, and it needs an input, and it needs something defined. So input is overloaded here, right? So instead of thinking of input to the function in the class, think of the input as the entire class itself, right? That makes sense? Right? So you have to look at the entire object that is being processed. Yeah, so good question. It's a bit subtle. So, right? So when I think of finding on a linked list or finding on an array or whatever, inserting an array or deleting, the input is not just the element I want to insert, but rather the entire linked list itself. Because if you think about it, the time that it takes depends on that entire object, not just on the element you're inserting. Okay? So you have, for example, you could plot this. So I could take another algorithm. Maybe I take TB of n, and that looks something like this. So how do I compare two functions? And that's really what the asymptotic analysis is about. How do I compare two different functions? So you know how to compare numbers. And so the question, and that's what all of this theory is about, is it's how to compare functions. So for example, if I gave you this function and this function, you'll probably say that this is bigger than this function. Like, so if this is function f and this is g, you'll probably say that g is greater than f. Kind of. It's not obvious though, because initially g is less than f. But sort of what happens is if you take the limit as n goes to infinity, in the limit g is bigger. Right? So when we are comparing functions, we will compare them by sort of comparing in the limit. It's kind of saying like, as your input becomes really, really large, which algorithm is faster or slower? Which algorithm is going to take less operations as the input becomes really large? Because when the inputs are small, maybe there could be sort of strange behavior that I don't want to deal with. So the way that, okay, so am I making sense here? Okay. So the idea is that Ta of n, or might be, an ill-behaved function. What do I mean by an ill-behaved function? It's like a function where derivatives may not be well defined. It might do strange jumps. It might do lots of zigzag behavior, things that you typically do not see when you're dealing with a function in mathematics. What I want to do is I want to compare this function with a nice benchmark function that I will refer to as b of n. So the benchmark function, what is a nice function like n squared, log n? Essentially think of it as like polynomials or logs or exponentials, e to the n, like functions that you will see usually in like a calculus course, right? So what you want to do is try to compare your ill-behaved function to a nice function. And you want to see how does these functions compare with a nice function so that we can sort of relate the running time. And the way this works really is we look at the limit as n goes to infinity of Ta of n divided by Bn. So okay, so we say in the limit, is your function less than the benchmark? Is it equal to the benchmark? Is it more than the benchmark, roughly speaking? So what happens when you take this limit is there are actually three possibilities. So the limit could be 0. It could be a constant that is not equal to 0, or it could be infinity. Now, technically, there are situations where the limit doesn't exist. Does anyone have an example of a function where a limit does not exist? Give me a function such that the limit as n goes to infinity does not exist. Yeah? Okay. So what's an example? If b of n approaches 0, the limit will become infinity. Sorry? It's still infinity. The limit is still, so what is the limit of n as n goes to infinity? Infinity. Infinity over infinity can be ill-defined, but give me just give me an example of a function. Like it was already said, what is an example of a function? Yeah? Sin n. Right? So this limit this is not defined. The limit does not exist. Yeah? What about this limit? What's that limit? Limit of n goes to infinity is sin n divided by n. Wait, I'll pause. Like, think about it. Give you a couple minutes. What is the limit? Who thought that instead of like, who thought this is what we're going to be doing today? Oh, wait, yeah. Yeah, what's the limit? What's the limit? Does someone know what the limit is? In the back, yes? It would go to 0, I believe. 0. Infinity goes higher than that constant is so large at the top is irrelevant. Exactly. This limit is 0. Why? Because this function is going to look like this. So in the limit, it goes to 0. Yeah, how many people are following what I'm saying? Like, raise your hand if what I said made sense. Okay, good. So there are situations where limits don't exist. But I'm going to assume that this limit always exists. In all the examples we'll consider, the limit exists. Okay? So let's not worry about the limit not existing. Maybe you never even thought that that was a possibility, but I have to be mathematically precise. So there are three possibilities that we'll consider. The limit is 0, the limit is a constant, or it's infinity. So what we're going to say in this case Now I'm going to write something here which is somewhat imprecise, but we're going to say then in that case T of n is less than B of n. In this case, we'll say T of A is equal to B of n, and its infinity, we'll say it's greater than the benchmark. Now, we're not going to use this notation explicitly. We'll replace this by what's called O and omega and various other things. But the intuition is if the limit goes to 0, that means the rate of growth of Bn is much larger. So the benchmark is much higher than your function. If the limit is non-zero, but it's a constant, then it's like the rates of growth are basically the same. And in this case, the third case, the rate of growth of T of n dominates the rate of growth of the benchmark. So T of n is larger. So it's the same thing over here. If you look at this example, the rate of growth of sine n is dominated by the rate of growth of n, meaning that n is larger. So you can actually say that sine n is less than n, although it's obviously not true. For small values of n, sine of n is more than n. But in the limit, sine of n is less than n. Okay? So whatever I'm saying here actually has nothing to do with the fact that TA of n is a running time. Whatever I'm saying here actually holds for all non-negative functions. So all of this notation is just about functions. This comes from calculus. We use this to talk about algorithms. Okay? A big point of confusion is people think big O notation only talks about running time. But big O notation is about functions. So in these cases, both of these cases, which means the limit is 0 or a constant not equal to 0, which means the limit is less than equal to 0. In this case, we'll say TA of n is O of Bn. Okay? This is what we write this. You read this. The way this is read is you say TAN is big O of Bn. This is the way you write it. This is now standard. This is the way people write it. Although before this was considered improper, technically what was written was TA of n is an element in the set O of Bn. But this is, nobody writes this anymore. Because technically, again, just technically, O of Bn is actually a set of functions. It is the set of functions such that this limit is at most a constant. O of Bn is the set of functions such that there's a set of functions TA of n, so the TA of n divided by Bn, the limit is less than a constant. Again, another technicality, this is not the correct definition of big O of n because the limit might not exist. And when the limit does not exist, there is a more technical definition you can give. Okay? But that's what's given in CLRS. You have this sort of more complicated definition using like something called C and N naught. But for all the cases that we consider in this course, this is enough. This is good enough. Yes?
How do we do the calculation TA of n over B of n if TA of n can't be mathematically modeled?
It's a good question. So we'll get there. So we'll talk about what, you can say if you don't, so the thing is you cannot pin down TA of n exactly, but often you can give upper bounds for TA of n, and that's good enough for computing an upper bound on the limit. So think of it as, I don't know what TA of n is, but I know that TA of n is less than f of n all the time, and then the limit is at most f of n divided by Bn. And if, okay, good question. Okay, so this is what big O notation means. So if you're ever confused, like what does it mean? Go back to this picture. And this is what it means. So again, the reason I'm doing this slowly is even though many of you have seen big O notation, I don't know if you've seen it in this way. Okay? Is this new? Raise your hand if this is new. Okay, right. So this is, in some sense, a proper mathematical definition when the limit exists. Yeah?
Why do we define it as if T of A is
good question. So I will answer that shortly. You're saying that, so that's actually a big point of, okay, I'll answer it and then I will qualify my answer later on. That's because people misuse the O notation and think that it's big theta, which is something different. Okay, so let's, okay, so you have these situations here. Now, TA of n is O of Bn if it's in any of these cases. If it's only in this case, technically, what is written is little o of Bn. If you've ever seen the little o notation, although we don't use it in this course, well, I don't think we'll ever use it in this course, but if you ever see it, it's when the limit is 0, it's actually little o of n. When the limit is a constant, then actually we write TA of n is theta of B of n. When it's theta, what this means is that these functions are basically the same up to constant factors. And in this case, often we write TA of n is little omega of Bn. I want to emphasize that all of this notation is just talking about comparing functions. It has nothing to do with running time explicitly. Okay? So I'm going to write this out again. This takes some getting used to, this notation. So I want to write this, I'm going to sort of rewrite this in a more cleaner way here. So I'll just say there's two functions t and b. All of these are, the fact that I call them t or b is irrelevant. This is natural numbers to natural numbers. So think of t as running time, and b as a benchmark. Again, this is the way you should think about it, although the notation has nothing to do with it. You can do this for any two functions. Yes? Running, sorry, that was a mistake. Running time. Yeah, running time, sorry. Okay, so this is a definition. Okay, so if the limit as n goes to infinity of t of n divided by bn, if this limit is strictly less than infinity. What this means by strictly less than infinity is that it's a constant or it's 0. It's a non-zero constant or it's 0. That's what I mean by less than infinity, right? The limit exists and the limit is not infinity. Then we say t of n is big O of b of n if the limit as n goes to infinity of t of n divided by p of n is greater than 0. What this means is it's not in this case, but it's in these cases. So again, there are three cases that can happen, but you can group them into pairs. You can say maybe both of these happen or both of these happen. Then we say t of n is omega, big omega of b of n. And if the limit n goes to infinity, t of n divided by b of n is a constant which is not equal to 0, then we say t of n is big theta of b of n. This is what you need to remember. Right? All of these pictures are there to help you, but this is the definition. Again, the definition is when the limits exist, but we will always assume that the limits exist. Yeah?
So is the point of the theta and omega just to kind of measure the accuracy in which direction it is, like if it's slightly better, slightly worse?
Yeah, so actually, theta is considered a tight bound. O is an upper bound. Omega is a lower bound. So the way to think about this is like saying less than equal to, this is like saying greater than equal to, and this is like saying equal to. Just as when you compare numbers, there are only three possibilities when you compare any two numbers, right? Less than, greater than, or equal, which we'll say is, or you can say less than equal to, these are actually they're overlapping cases, but you can say two numbers, they're less than equal to, greater than equal to, or equal. There's O omega theta. So at some level, all of this is simply saying that just like you have ways of comparing numbers, you have ways of comparing functions. That's what O, omega, and theta are. The little o, little omega are often, they're used, but this is what you will commonly see as a CS undergrad. Or most often you see O. And many people, when they say O, they really mean theta. But you should not make that mistake. So you'll see people saying merge sort is an O of n log n algorithm. That's true. Merge sort is also an O of n square algorithm. Because O just means it's greater. Right? But often people won't say, people say, no, merge sort is not O of n square, it's O of n log n. But actually, O of n log n means it's also O of n square. Just like saying that if something is less than 100, it's also less than 1,000. Okay? Questions? Now, I'm going to start asking you questions, then see how well you understand, right? It takes some getting used to. But again, if you ever get confused, I recommend that you go back to this picture here, or this writing and this picture here. The limit only has three possibilities: 0, constant not equal to 0, or infinity. And depending on which of these cases, we say, O omega theta. Although we club these two cases together, and we club these two cases together in O and omega, and this middle one is theta. Okay? Now, you might say, how am I going to use any of this for algorithms? And we'll come to that. But first, let's make sure that we understand this notation. Yes?
So is the reason why it included and can also be used is because all algorithms worse than the benchmark will be included in omega, and all the algorithms that are in the O, like every possible one?
Yes, yes. And every algorithm that meets the benchmark is in theta. Right? And so, again, this can be used for any sets of functions, as I described, but commonly, this will be a running time, and the function that sits in this is usually some well-behaved function, like n log n, n squared, log n, exponential in n, or something that you see that you can mathematically manipulate. Okay? All right. So I'm going to leave this over here. Now I'm going to ask you a series of questions to determine how well you understand this. Question. So in all of the questions that I'm going to ask, I'll just think of t and b as two different functions. Okay? T and b as two different functions. First question is, can t be O of b and t be equal to omega of b? Question. And again, by t, I just mean t of n, right? I'm just going to drop the n from there. And so the answer is yes. So b is overloaded here. You know what I mean. This is blue. No, I'm not being facetious here. I mean, like, I really want to understand, like, are you following? Does this question make sense to you, or does this look like some random gibberish, right? So, okay, I'll give you a minute to think about it and then answer. Can both of these happen simultaneously? Okay, so what's the answer? Yeah, okay, so I mean, I don't know what it means to pick up two post-its. There are some people who might be a little confused. Okay, the answer is yes, it can be. But anyone who's confused should pause and maybe ask me what their confusion is, if they can articulate it. Unless you're at this, there are many stages of being confused, right? One is I'm confused and I can articulate my confusion. And one is I'm so confused that I cannot articulate what is it that's confusing. And then there are even deeper levels where I cannot even articulate the fact that I cannot articulate the fact that I'm confused. And you can do this inductively. But okay, so yes, this can happen. Because what t is equal to O of b means the limit is less than infinity. T is equal to omega means the limit is greater than 0. Can both of these happen simultaneously? Yes. And when that happens, the limit is actually a constant, which is non-zero. For example, if t is equal to b, then the limit is 1, which is less than infinity and more than 0. Yeah? All of these can happen simultaneously. When all of them happen simultaneously, then this is happening. Right? I should maybe point out that if you go back to this slide, these three cannot happen simultaneously. Right? They're actually exclusive cases. 0, non-zero, infinity. So technically, little omega, little o, and little omega cannot happen simultaneously. But big O, yes. Yes? I'm sorry, which last condition? This one? You want an example where that could happen? This one. You want an example of where this can happen? Okay. So suppose t of n was actually equal to b of n. The functions are identical. Then the limit as n goes to infinity of t of n divided by b of n, this is just going to be 1. Right? Now 1 is a constant that is non-zero. So it is theta. But also note that 1 is less than infinity. So it's also O. 1 is greater than 0. So it's also omega. So all of these, it's like saying that if I have two numbers that are equal, they're equal. One is less than equal to the other, obviously, and one is also greater than equal to the other. The confusion with these cases is they're not exclusive. They can all happen simultaneously. Whereas when you use the little o, little omega notation, they're actually exclusive. So some might argue that maybe this is better because but commonly this is what is used. So don't worry about the little o and little omega. These can happen simultaneously. Again, O is like less than equal to, omega is greater than equal to, theta is like equal to. Yes? Yes, exactly. So I'll do more examples here, and I think it should clarify. So I'm going to do like a series of questions, and hopefully then a lot of this will be clearer. Okay, so here's another question. Is n equal to O of 5n plus 3? Yes. No. This is confusing. Okay, I'll give you another minute to answer this question. Is n equal to O of 5n plus 3? Yes or no? If you're confused about any of this, take the limit and you'll see the answer, right? The point is, if you're trying to look at it and just like saying, is the answer going to, is it going to hit me? It might not, but if you take the limit, you'll see the answer. Okay, yes, what's yes or no? Okay, so those of you who have answered have it. The fact that fewer of you are answering suggests that more people are confused. Okay, so how do we determine if this is the case? You have two functions here. This is like t, and that function is like b, right? So we'll take the limit, as n goes to infinity of n divided by 5n plus 3. Okay, now you've all done a calculus course. What is that limit? Oh boy, okay. All right. What's the limit? Exactly. 42 is always the right answer. It's 1/5, right? Right? Take the limit. It's 1/5. Is 1/5 less than infinity? That you should be able to answer. 1/5 is less than infinity. Is less than infinity, so it's O. Just do it syntactically, right? Don't just take the limit and see what you get. That's all. Okay? Question. Is is 5n plus 3 O of n? Same, yes, no. Take your time, answer. Think about it. Take the limit. Compute the limit. Okay, what is the answer? Yes, right? It's yes in both cases because, again, you just take the limit. Limit n goes to infinity 5n plus 3 divided by n. What is this limit? 5. Good. You're all waking up now. Or at least whatever knowledge of calculus was buried deep inside your neurons is slowly emerging. Yeah. I have a rant about calculus education, but I'll get to that later at some point. But the point is, just take the limit, right? That's all. Question. Is 5n cubed plus 15 O of n squared? Question. Same options now. Yes, no, confusing. And if it's confusing, you should raise your hand, because the more people who raise their hand saying confusing, the slower I will go and explain things. If I see that everybody understands, I'll just proceed. Okay, so take your time. I'll give you a minute. Take the limit. This function divided by that function. Take the limit. Question? Let me answer in a while. I can't hear you. Yes, what is the answer? Okay, yes, it's blue because you take the limit as n goes to infinity of 5n cubed plus 15 divided by n square. And note that that's a cube divided by a square. This limit is infinity. And because it's infinity, it's certainly not less than infinity. So it cannot be. So this is no. So someone had a question up front. You had a question. 5n plus 3 on top over here. Because when you're doing, is the left-hand function equal to big O of this? So this is like t, and this is like b. So it's t divided by b. When you're doing this case, it's n divided by 5n plus 3. When you're looking at this, it's 5n plus 3 divided by n. Does that make sense? The function that's in the O is the denominator. So that is in the denominator here. That is in the denominator there. Yeah? Yes? Say it again? Okay, so if you set this to be little o, it would still be no. Little o means that the limit is 0. I'm sorry? The little omega, you mean? It is little omega, yeah. Yes? Okay, so let me write something here and then maybe it'll clarify that. So this is not true. What this means is what? This function is greater than or equal to this function, which kind of makes sense, right? So the question now is this true? Again, yes, no, confusing, same options as before. Is 5n plus, yes? Yeah, what's the answer? So it's yes, because now when you take this limit, we know the limit is infinity, and infinity is greater than 0. And so it's omega. So the answer there is yes. So the thing is, it's not a good upper bound, but it is a lower bound. It's like saying the benchmark is not above it, but it is below it. But it is not theta, right? So again, 5n, is it equal to theta of n squared? No. Why? Because the limit is infinity, and infinity is not a non-zero constant. So it is not theta. Okay? We'll do one more. We'll do one more easy one, and then we'll do some hard ones. Is n big O of n divided by 100 minus a million? Yes, so what is the answer? Okay, so people are still processing it. I'll wait, give you a few minutes. Okay, so what is the answer? Yes, again, you would see that this minus 10 to the 6 has nothing to do with the limit, because as n goes to infinity, this doesn't matter anymore. Yeah?
Would you ever want to benchmark against something weird like that?
No, you would. No, you wouldn't. You would not benchmark against that. But the reason I give these examples is to tell you that the notation has nothing to do whether anything is running time or a benchmark or anything. Like this notation is there for functions. We will use it in a particular way, but the notation makes sense for functions, and anytime you're confused, you go back and compute the limit. Right? Anytime you're like, is this O, is this omega? Look at this picture, compute the limit, and you'll see that in all the examples that you'll ever get, the limit is really easy to compute, except for the next one that I'm giving. Okay, so maybe I'll keep this. I'll keep this here. Now I really test you. Yes. If you wanted to find the optimal benchmark, that's what you would do, exactly. But sometimes finding that optimal benchmark is difficult. Like there are cases where maybe it's like an open problem in math to find the right benchmark because you don't know exactly how the running time behaves. But yeah, that's exactly. Okay, question is, log base 2 n. Oh my God, everyone's like log. What was the definition of the log, right? Okay, is log base 2 of n O of n? Right, again, red is yes, blue is no, green is confusing. Okay, I'll give you a minute. Now you need to do some limit calculations here. What is the answer? Okay. Some of you have yes, maybe a few no's, but there are very few people who are answering. So what about the rest of you? Okay, so the answer is yes, just to get that. How do you do this? Yes? Slowest, well, I can give you a function that increases slower than log n. So you've stumbled your way onto the right answer. But what should you do? Sorry? Okay, I guess you could draw a picture. Why do I have this slide up here? Compute the damn limit, right? Just compute the limit, right? It's not that, well, okay, maybe it's a little harder. So who computed the limit? Sort of, kind of. So few of you. Yeah. That is the right answer, right? I mean, the reason some of you might say that's true is because you've done some CS course before where you've kind of been told that, oh yeah, logs grow slowly. There are functions that grow slower than logs. Give me an example of a function that grows slower than a log. Yeah. Constant. There you go. Give me another function. Yeah. Exponential decay. Okay. That's another function that grows slower. Although that function is not from integers to integers, but yes. Give me a function that from integers, well, okay, even this is not integers to integers, but square root of log n. Right? Yes? Why? Yeah, good. Why? Yes, but what is the rate of growth? Tell me. So how did you compute the limit? Yes. L'Hopital's rule. Good. I should have candy or something and like give you candy. Yes, use L'Hopital's rule. Exactly, right? Exactly. Okay, then what happens when you do L'Hopital's rule? Okay. Okay, you're 90% there. You had the right idea. Yes, the derivative of log base 2n. Okay, it's not exactly 1 over n, but it's like a constant times 1 over n. Right? It goes to 0. Okay, so what you do is you take d by dn log base 2n divided by d by dn of n. So that's one. Well, let's have some fun with this. What is that thing? Come on. How many courses of calculus have you done? Have you done calculus from high school? 3 courses of calculus in college. In high school. 3 in college, 1 in high school. So you've been doing calculus for at least a couple years. Now I will complain about your calculus education. It's not your fault, by the way. I'm not blaming you. I'm blaming your calculus education. No, it's true. Like, you're smart enough to understand all of this. Yes? Say it again. Let's give him a round of applause, please. Thank you. That's right. I'll bring chocolate from now on for that. So you take the limit as n tends to infinity of that. So it's the limit n tends to infinity of 1 divided by n, the natural log base 2, which is 0. So this limit is 0. So I'll rant a little bit about the log function. So you've probably seen log base 10, right? Nobody uses log base 10, right? Actually, does anyone know why log base 10s have ever been used? You have yeah, you have 10 fingers. But what do you do with log base 10? Yeah?
Isn't it like exponential notation? You can do easier calculations with it.
Yeah, so there are these things called log tables, which use log base 10 so that you could actually multiply numbers more quickly. You may have never seen a log table. Like you may not even know what a log table. Have you ever heard the term log table? No. You have. Somebody else says. You've seen a log table. Have you ever used it? You haven't used it. No, it's a bummer. You have used the log table. Huh? In elementary school. Okay, so. Oh, okay. So, yeah, I had to use log table. I mean, it's ridiculous. But the only logs that actually matter, there are only two logs that matter. There's log base 2, and there's the natural log, which is log base e. So in all computer science applications, log base 2 appears. And in most math applications, log n appears. And log base 10 only appears in high school. It's the only place where log base 10 ever appears. So you should purge it from your memory, right? Log base 10 is unimportant. The only thing that's important is log base 2 and the natural log. Okay? So why? Okay, now I'm going to ask you another question. Completely random, right? Okay, so an amoeba divides into 2 each day. Make sense? So you have an amoeba, it splits into 2 every day, right? And so every day each amoeba splits into 2, right? That's how these things grow. Okay? So we'll say day 0 has a single amoeba. How many days to reach n, I guess it's amoeba. Does question make sense? Right? So forget big O, omega, linked lists, everything, right? You have an amoeba. Every day it divides. So each amoeba divides into 2, right? How many days is it going to take to reach an amoeba? I want you to work this question out. I'll give you a few minutes. I'm sorry? pH is log 10. That's true. Chemistry. Chemistry. I stand corrected. Chemistry has a log base 10 use. It was, yeah, exactly. Yeah, so how many days to reach an amoeba? How many of you know what the answer is? Okay. All right, some of you. There's a reason I'm asking this question at this point, right? I mean, it's not completely random. It's sort of random. Okay, so honest answer. Raise your hand if you have no idea how to approach. Like if you're quite, yeah, good. No, raise your hand if you're not sure how to do this. See, that doesn't add up, right? There are a few people who know the answer and a few people who raise their hand saying that I don't know how to do this, and the rest of you are, some of you are asleep, I can see, but not all of you. I can see the ones who are asleep. Don't worry. You should tell the people when they wake up that I can see. But okay. So let me just tell you why this is important and why this is related to all the things we're doing. So first, obviously we've dealt with a pandemic, right? And you've seen projection numbers where they say, oh, like people are, in so many days, so many people get COVID, things like that, right? Okay. Have you heard of something called the R number, which is often used, right? And what is it that they would say? When the R number is more than 1, then we're really in trouble, right? How are they doing these projections? It's not that, so there's some statistics, but it's not that difficult. It's very similar to this. The R number is, instead of an amoeba dividing into 2, it would be that one person would infect that many more people, right? So if the R number is 1, then one person just stays as 1. If the R number is like 1.5, it means that, like, on the average, if you have X people with COVID, the next day you have 1.5x people with COVID, right? That's what the R number is. That's the replication factor. So for the amoeba, the replication factor is 2. So what is the answer? What is this answer? Does someone have the answer? Yeah. Log base 2 of n, right? This is log base 2 of n. And this is really important that you understand this, because that's what the log function actually means. So on day I, we have 2 to the I amoebae, right? And so when do we have n? It's when 2 to the I is equal to n, right? When I reaches the number such that 2 to the I is equal to n, you have n amoebae. And this is exactly log base 2 of n. Does that make sense? This logic is going to appear many times. But what I would like you to do is, if you've ever been confused about the log function, this is really what the log function means. The base over here is the replication factor. So if it were dividing into 4 each day, you would get log base 4. If it was dividing into 1.5, what I mean by 1.5 obviously is that half of them divide and half of them don't, right? Which means the number goes up by 1.5 and the base is 1.5. So in COVID projections, that base was the R number. And that's how they did projections. Okay, so, and does this sort of kind of make sense? If you got nothing from today's lecture except this, I would still be happy, right? At least you now know what the log base 2 function means. When something is doubling, how long does it take to reach a number? That's the log function. Is that clear? When something doubles. Okay. Let's take a break for a couple minutes, and then I will ask you more painful questions about the log function. All right, so let's go back to the log functions. By the way, I stand corrected on the log base 10, as someone pointed out. pH, the pH value is based on log base 10. So, yeah. Isn't what? The decibel scale. That's a good example, yes. Decibel scale is also log base 10. Yeah, that's true. Richter scale is log base 10. That's right, Richter scale is log base 10. But all of that is, it's a mistake, right? It should all be log base 2 or natural log, because mathematically, log base 10 sort of never appears. Maybe I should say mathematically, it doesn't make a natural appearance. Natural log makes a natural appearance. That's why it's the natural log. And that comes about because E makes a natural appearance. Log base 2 appears in CS a lot. So much so that in some books, there's the notation LG for log base 2. Usually when I say log, I usually mean log base 2. Okay? And so this logic over here, again, remember, log is the opposite of exponential, and it's all about, think of it as that's the growth rate, and the log is the number of days it takes with a particular growth rate to reach a number. Right? This is the exponential, which is the number of amoeba. Right? So you have these three quantities here. The growth rate, the actual number of amoeba or number of objects, and the number of days it takes to reach that number. Does that make sense? So this is a useful example to sort of have in your mind to think about the log function. Speaking of which, I have another question now. Is log base 2 of n O of square root n? Need I say this again? Compute the limit and use L'Hopital's rule. There, it's there. Does anyone have the answer? What's the answer? Still working on the limit? Still working on the limit? So work out the limit then. Work out the limit. And let me, for your help, also put that down over there so that you can see the derivative of log base 2 of n. Okay, so what's the answer if some of you have it? That's right. That's right. The answer is yes. So again, I won't work the limit out entirely, but you'll see that log base 2n divided by root n, the limit as n goes to infinity is d by dn log base 2n d by dn of root n. Again, the limit n goes to infinity. Okay, what the heck, I'll just work it out. So here you get 1 divided by natural log of 2. And what do you get here? What is, yeah? 1 half, yeah. Essentially you get 1 divided by 2 root n. Right? And if you work this out, what you get is, you get some constant here, right? The constant is like 2 divided by log 2 times 1 divided by square root n. and this is now 0. So this exemplifies an important principle, is that the log grows slower than any polynomial. Okay? Yes, it is one of the slowest growing functions, but you need to know why. You need to know why, and the reason is calculus. I know, of course, I teach this course. I know this, but you need to know it. Right? So the derivative is the answer. So therefore, n log n versus n to the 1.1, this is smaller. The reason it is smaller is, again, the same logic. Instead of root n, even if you put n to the 0.1, the same logic will hold. Okay? This is not so obvious that n log base 2n is better than n to the 1.1. But, okay. Final question on the log is log base 2n theta of log base 10n. What's the relationship between these things? Again, take the limit, and you'll see. Right? So it's change of base. You have to use the change of base rule, and you'll see the answer. Okay, again, that's right. The answer is yes, because log base 2n divided by log base 10n. So let me do a change of base on log base 2n. If I do a change of base, I get log 10n divided by log 10 base 2 divided by log 10 of n. Right? So these things will cancel out. I get 1 divided by log base 10 of 2, which is the same as log base 2 of 10. It doesn't matter. In any case, this limit, even if I take the limit is a constant. Right? And because the limit is a constant, it's theta. What this says is also quite interesting. What it says that if the growth rate changes, the number of days, so let's just go back to this amoeba example. So instead of 2, it was 4. What this means is that, okay, so how do I put this? The number of days that it changes will only change by a constant factor. Right? The growth rate affects this, but it only affects the number of days by a constant factor. So anyway, okay, so that was maybe not very well said, but hopefully you understand all of this, right? So we've covered a lot. What you need to remember from today's lecture is you need to remember this, or you need to understand this, yes? Sorry, say that again? You could just replace it with any constant you want, and the most common constant to use is 2. Right? So that's why you'll see that it'll just say O of n log n, and often they won't even specify the base, because the base doesn't matter with respect to big O notation. You could change the base, and it only changes things by a constant. So it doesn't matter which base you use. You can use usually use natural log or use log base 2. And in CS, you would use log base 2. So that's why often they'll just even say log and not put a base there, because it doesn't matter. Any constant is fine. Right. So we have the definition of O, omega, and theta. Again, as I said, this is talking about functions. There's nothing about runtime here. So please make sure that you understand this. Go over these questions that I gave you. All the slides will be made available. Make sure that you understand the answers to all of them. Understand the log function, because the log function will repeatedly appear as we're doing analysis of algorithms. Okay? The reason why I care so much about the log base 2 is because we see it over and over in this course. And the important things to understand about the log base 2 are, again, go back to this example. That's what log base 2 means. And these examples tell you that the log grows slower than any polynomial. So it's a very slow growing function. right? Any questions about this? Yes, no? Okay, it's a lot, I know. Again, it takes time to understand the big O notation, right? You can't just see the definition and have it in a day. To go back, read about it, make sure that you look at the notes, try to solve all those questions. If you read CLRS, the discussion there is a little more complicated because it gives a more technical definition of what the O notation is, but it's just the same. Always take limits. If you're confused, take limits. That's the answer. Okay. So we have like less than 10 minutes left. So obviously, I don't want to do anything complicated, but I would like to connect all of this discussion that we had with algorithms, which is sort of the point of this notation. And so let's go back now. Let's go back to linked lists. And now we can ask this question of how long, or really what is the running time? What is the running time? How long does it take to find an element in L? Right? This is sort of the question that we sort of kind of started with in the beginning. How long does it take to insert? And by how long, I can now define this function where T of n is the worst case running time of inserting, of find in a list of length n. So this is, again, n is the size of the list. So as we argued, this function, let me go back to what I had. Here was the function to find. As we said, the number of elementary operations, it might be 3 times n, it might be 4 times n, depending on how you do it. Maybe it's 4 times n plus 1. In some cases, it will be much smaller. So instead of trying to pin down exactly what this function looks like, we will just compare it to a nice benchmark function. And so the question is, I'll say, what is the right O bound? So is T of n O of 1? Is T of n O of log base 2n? Or is T of n O of n? Right? What is the right bound? And this, again, this might be things that you're familiar with if you've seen from before. Okay, so what is the answer? That's right. It is O of n. This is something that you're all familiar with. And the reason for that is you know that you might have to traverse the whole list. Now, the question is, what is the right omega bound? Is it T of n is equal to omega 1? By right, I usually mean the best. T of n is equal to omega log base 2n is omega of n. Think about this carefully. So what is the best, what is the right omega bound? What is the answer? It's often a point of confusion on this. It is omega n. It's not omega 1, even though, okay, now here you have to be careful. The best case for find is constant. But T of n is the worst case runtime. We're looking at a lower bound on the worst case. Okay? Omega does not mean best case. Best is let's remove that word there. So, no, there's a confusion that omega is like the best case runtime and O is the worst case runtime, and that's not true. We are always looking at the worst case, but we're trying to benchmark the worst case. So O is like I benchmark from above, omega is I benchmark from below. But what we know is in the worst case, it actually takes like n operations. You have to go through the whole list. And therefore, it's both O of n and omega n. It's actually theta of n, right? So T of n, in this case, is theta of n. Yes? Yes, there are data structures, and the reason to do all of this is so that now we can talk about data structures